بسم الله الرحمن الرحيم. We finished last time a motion in a uniform circular motion, or Newton's laws on uniform circular motion. Now we add a little more complications. What is that? Well, non-uniform circular motion. And when we say non-uniform circular motion, that means the speed will change. The speed will change. So previously, velocity only was changing and speed is constant. So we have only the radial component or the centripetal component of the acceleration. Now we add a little bit more complications. That is, the speed also is changing, so we will have a radial part of our acceleration that is will come from v square over r, and now we have a tangential acceleration that we discussed before, because speed now is changing. So be careful here, there is a mistake. This is tangential. So radial plus tangential. So now the total acceleration is the sum of two vectors, the radial vector and the tangential vector. So net force now is the sum of forces in the radial direction and forces in the tangential direction. So this is tangential due to changing in speed, and this is radial, that is centripetal. طيب. So previously we talked about this example where we have constant speed, velocity is changing, but the speed was constant. Now let's talk about that speed is changing. So previously we studied the normal force at the top and the normal force at the bottom. Now let's assume that we don't have a seat that is fixed. Let's assume that we have an object and it is attached by a string. So we have tension instead of normal force. That is keeping the body to go into a circular motion. And let me remind you all that in a circular motion, you need something to provide the force, to force the object to go into a circular motion. And that could be a string, could be friction, could be gravitational, could be magnetic, could be electric, you name it. So there must be some force that will force the object to go into a circular motion. Other than that, the object will just go straight forward. The object will go straight forward. So let me just redraw this diagram. Exactly the same, but I will do it step by step to make it clear. So we have our circular motion. We have a string, and attached to that string we have a ball, and it's moving in this direction. It will reach here at the bottom. So here is top, and here is a bottom. And as a result, So here we have velocity 2, here we have velocity 1. It is changing in magnitude and direction. Changing in magnitude and direction. And now let's talk about the general case. So this is R, and this is R. So what are the forces here? Well, we have tension, and the tension is keeping the ball going into a circular motion. And now we have mg. That's the gravitational force. So we analyze this mg into two components. So this is theta. So this is mg cosine theta. And now perpendicular to that, I have mg sine theta. Exactly like this one, but I went into 2 steps or 3 steps just to make it clearer. طيب, where is the physics in this situation? Well, the physics is as it follows. Now, because the component is mg sine theta and mg cosine theta, that means this one and this one are always changing in motion, changing in value, always changing in value. Previously, in a uniform motion, you have a sturdy structure, so it will force the object to go into a uniform circular motion. يعني it will force the object to go into a constant speed. Now it's only a string, so mg sine theta and mg cosine theta are always changing. And as we said, the total acceleration must equal the tangential acceleration plus the centripetal acceleration, and he is calling it in the book the radial acceleration. So I will just use it in order to reduce the confusion. So, but I will write here. This is the centripetal acceleration, which is equal v square over r. And v is always changing. So the centripetal acceleration is always changing. Okay, what else we can write in terms of physics? Well, here, look at the tension. We have the tension minus mg cosine theta. Here is the tension, and here is mg sine theta. So it's a minus sign, and that's not equal to m v square over r. So the net force.
دكتور معلش بس الجزئيه بتاعت الكوساين والساين لسه قاعد بخبط فيها انه على اساس احط هون ساين ولا هون كوساين.
مش فاهم عليك يا شيخ، ايش اللي بتخربط فيه؟
في الرسمه انت حطيت على الناحيه اليسار كوساين والتحت ساين.
طيب
بعض الامثله بتكون اليسار ساين وتحت كوساين، على اي اساس بتصير هي؟
على اساس الاسهل لك في الرسمه. اللي أسهل لك في ال problem. What is the easier for you when you analyze your problem? Depends on what is easier for you. Well, كيف تحدد with experience. When you solve one problem and after a problem and after a problem, you decide with experience. يعني this you can write. I hope I will not confuse your colleagues. Let's say this is alpha. So then this one will be mg cosine alpha, and this one will be mg sine alpha. And then you do your calculation or writing your equation. It won't make a difference, because you want to write the component. And if I can help it, I can just see this is theta, this is mg, and this is theta. So this is mg cosine theta, and this is mg sine theta. If you want to look at like this, and now we are talking about alpha, so this component now is mg cosine alpha, and this is mg sine alpha.
دكتور هو على حسب اختيار الزاوية
على حسب
اختيار الكوسين والسين.
صحيح، حسب الزاوية، وبعدين how you want to analyze your components. It's always how you want to analyze your components. So this is equation number 1. That's the physics. That's the beef in this problem. Yani this is how you get the marks in this problem, in this kind of problem. Are you able to write this equation? It is tension minus mg cosine theta is equal mv square over r. And we know that the tangential acceleration, اللي هي centripetal acceleration, it's the same. We are just using two different words for the same thing. Must equal v square over r. اتفضل يا عبد الرحمن.
دكتور how is the tangential equal to the centripetal?
عفوا، مين البطل هذا؟ والله شكرا يا عبد الرحمن. This is radial. شكرا. هلا the book is يعني الكتاب مولع في ال derivations. يعني I can rewrite this as t is equal mg cosine theta minus plus m v square over r, and then I can simplify it a little more. I can take mg out, so I end up with cosine theta plus v square g over r. But it won't make a difference. The important thing is, can you write this equation? And then after, depending on your problem, you can decide what to do with it. But that's the main beef is here. The main beef is here. طيب. Now let's move on to relatively new thing, new subject, اللي هو motion in the presence of resistive forces. Motion in the presence of resistive forces. يعني مثلا you have a picture of a fish. A fish swimming in the water. You have resistive forces. Or in reality, when you have, for example, a free fall, or an airplane or an object moving, you have air resistance, and these kind of forces that will prevent you from reaching or utilizing your total force. Resistive forces, we have two kinds or two models. The first model, in a resistive force, is proportional to the velocity of the moving object. Proportional to the velocity. And this we can apply on two conditions. Condition number one, that the velocity must be small. That's the first condition. What is the second condition? Second condition, in the diameter of the object or dimension of the object also small. In this kind of motion, the resistive force is proportional to the velocity of the moving object. We are not discussing that, not the laminar and the turbulent flow. No, we just looking at it from a different angle. It's just proportional to the velocity, and the second model, force, is proportional to the square of the speed. And in this model, when we are dealing with large objects. Large objects. A person in a parachute, for example, a car moving at high speed, these kind of systems, then we are talking about force proportional to the square of the speed. The first part, force, is proportional to the speed or to the velocity. Well, speed and velocity opposite in direction. Always the resistive force is opposite in direction. So let's talk about the first model. So the first model, we have an object moving in a liquid. Object moving in a liquid. Well, I think in your lab 192, you have an experiment talked about that. We call it viscosity. Viscosity. I don't know if it's still there, but we have viscosity experiment talking about this model. So we start with a sphere or any kind of object shape, and we let it drop inside the liquid, so it will move due to gravity inside the liquid. So at the beginning, V is 0. Let me just change that. It's blue and blue. So at the beginning, velocity is 0, and then it start to accelerate due to gravity. And as it starts to move with the velocity inside the liquid, you start to have a resistive force pointing up. pointing up. So when we want to apply Newton's second law, we have mg pointing down, and we have the resistance force or the resistive force pointing up, and the net force will cause the acceleration, and the net force will cause the acceleration. So this is a resistive force. This is a constant, B, just a constant, and it's different for each liquid. And can be determined by experiment. The object is applying the resistive force. The object is not applying anything, yeah, Yusuf. Gravity is pulling down, and resistive force is pulling up. But the object is not doing any force. The object is not doing any force. We have the force of gravity pulling it down, and we have the resistive force pulling it up. طيب, what is V? V is the velocity. Velocity. And we have also tau. We will come and explain it. We call it the time constant, and it is equal to the mass of the ball divided by B. So basically B is equal the mass of the ball divided by tau. The mass of the ball can be measured experimentally, and tau can be measured experimentally, so we can determine B from experiment. So each liquid has its own coefficient or has its own constant. هلا tau we define it as time constant to reach 63.2%, and we will explain it in a moment. Why 63.2 of its terminal speed. And what is terminal speed? Terminal speed, when summation of forces acting on the object is 0. Then we have V terminal. Yani when mg is equal R, and those are forces, mg is the gravitational force and R is the resistive force, then velocity is constant, and we call it terminal velocity. We call it terminal velocity. In reality, there is another force acting on the sphere in this situation, and that's what we teach in viscosity experiment. So let's just talk about it. The book is completely ignoring that force. So let's talk about it. So here is our sphere. mg pointing in this direction. And we have R resistive force pointing in this direction. And also we have a buoyant force. We call it F buoyant. Also pointing up. And that buoyant force is equal minus density multiplied by the gravitational acceleration multiplied by the volume of the object. So this is volume, this is G, and this is the density of the liquid. So in reality, there is also a buoyant force acting, but the book neglects that, so I am going also to neglect that force to make it just simple in analyzing the problem. Iman said, so this force is what causes certain objects to float. That's correct. And this force is always there. Even if the object does not float, the object net weight will be less because of the buoyant force. So, but I will just ignore it like the book, just to make analysis of this problem much easier. طيب, so let's come back here. So this is mg minus r is equal ma. Summation of forces is equal ma. That's the second law of Newton. And minus bv is our resistive force. So we rearrange this equation. So we bring ma is equal mg minus pv, and then we take out the m from this equation. We divide everything over m. So we end up acceleration is equal dv over dt, and g minus p over m multiplied by v. So this equation when you have a variable that is v, here we have the derivative of v and v in the same equation, we call this differential equation. So this is differential equation. And for most of you, I think you didn't cover that in calculus. It's a second year. I think you take it in second year. يعني don't worry if you, because you have, there is a full course called differential equations. I don't know if you are going to take it or not, but don't worry about this equation. Again, it's ma is equal mg minus bv. We take out the m, so we end up with a is equal g minus p over m multiplied by v. So we have a derivative of v on one side, and we have v on the other side In such a situation, it's a differential equation. It is called differential equation. And it has its own techniques to solve it. So if you didn't cover it in calculus, no problem. We won't ask you to do a lot. Just we need you to know that when you have a derivative on one side and you have the variable in the same equation, when you have derivative and the variable on the same equation, it's a differential equation and it has its own techniques to solve it and find the solution. Clear how I reach this equation, Dawood? Okay. So now we just manipulate this equation as follows. Remember, we said A is equal G minus B over M multiplied by V, and A is dV over dt. When we reach the terminal velocity, that means A must equal to 0, and then we change this to V terminal, as here. No, it's not maximum velocity, it's maximum constant velocity. يعني velocity will increase until it reaches its maximum value, and then after that it's constant. So you need to add to maximum velocity maximum constant velocity, يعني it will not change after that. It will not change after that. Okay. So then we have this equation, it's equal to 0. That means the terminal velocity is nothing but m multiplied by d divided by b. And b is a constant. B is a constant. So at terminal velocity, the solution of this equation, so this is the differential equation, the solution of that differential equation has to be of the form with an exponent. This is the form of the solution. And if you didn't take differential equations, no problem, just take my word for that. So when you have a differential equation like this, the solution of this differential equation has to be in the form with exponent. Well, what is mg over b? It's a virtual, I keep saying virtual. It's the terminal velocity. It's the terminal velocity. So this is nothing but the terminal velocity. We put it in the solution. So then in general, V, the magnitude of the velocity in this system, is the terminal velocity multiplied by 1 minus e to the power minus t over tau. And tau, we just determine it from experiment. And t is the time starting from the motion when you have the object moving inside the liquid. So we have this equation now. So let's find the value of tau. Well, this is V of tau, yani the speed of tau. We apply our equation. It's a terminal velocity 1 minus e to minus tau over tau, يعني e to minus 1, يعني 1 minus 1 over e. You do the calculation. This value is equal to this value. So this is how we define the terminal, the tau value. It is 0.632 of the terminal velocity, Don't worry if you don't understand the derivation, because you didn't take differential equations. To remove the ambiguity, I'm going to solve with you step by step. Just memorize, and even you don't need to memorize, because in the exam I'll provide you the equation. In the exam I'll provide you the equation. So because it's new for you, you never saw that before, I am going to go and solve this example with you. So I'll give you a minute, read the problem. So in this problem, we have a small sphere, and he gave us the mass, 2 grams. And of course, released from rest. And he gave us the terminal speed value. So this is the terminal speed. And finally, he wants the time, determine the time constant, tau, and he wants us the time when the sphere reaches 90% of the terminal speed. So we'll solve it together. Of course, it's solved here in details. But I will go with you step by step, since it's new for you. طيب, let's write the values. Well, mass is equal to 10 to minus 3 kilogram. Terminal velocity, or terminal velocity magnitude, is 5 10 to minus 2 meter per second. That's the magnitude. And where is the direction? It's pointing, of course, up. mg is pointing down. Terminal velocity direction. It's a terminal, so it's going down. It's going down because it's the terminal velocity. So the direction of the velocity is pointing in the same direction of gravitational acceleration. So he asks us the first part, determine the time constant tau. So what do we have? So he wants tau. Well, tau is equal m over b. We just wrote it here. Tau is equal m over b. So let's find b. Find b. But we know that also b from here. We know that b is equal mg divided by the terminal velocity. We have the value of m, yes. We know g, and we know the value of terminal speed. So let's put them in the equation. 2 10 to minus 3 multiplied by 9.8 divided by 5 10 to minus 2. And what's this value? Can somebody calculate it? أحسنت يا داوود. 0.392. Now we come back and use tau is equal mass divided by b. So that is 2 10 to minus 3 over 0.392. And that is equal كم يا داوود؟ مظبوط 5.1 10 to minus 3 seconds. So that is tau. That is tau. Any question? طيب, let's do the second part. He wants the time at which the sphere reaches 90%. B is a constant. So G here, when you find the value of B, is 9.8 because it's just a constant. And you can understand it also like what Dawood said. No, it's in the same direction of, يعني G is in the same direction of V terminal. It is not static friction. It is not static friction. This is a resistive force. Static friction is a force between two surfaces. This is an object moving through a medium, through a liquid. It's different than the friction force. طيب, let's change the color of the pen and solve part B. We have V is equal V terminal multiplied by 1 minus E minus T over tau. And from where we have it? From this law. We are talking about this one. So his question is to find time when it is 90% of the terminal speed. So that means 0.9 Vt is equal Vt 1 minus E to minus T over tau. V terminal is cancelled. So we end up 0.9 is equal 1 minus E t to the power E to the power T over tau. Well, that means E to the power T over tau, there is a minus sign, is equal 0.1. So 1 minus something is equal 0.9. That means this something is 0.1. طيب, so E to the power minus T over tau is equal 0.1, sorry. Yalla, how to solve this? Well, we have to take len for both sides. So len E minus T over tau is equal len 0.1 يعني E T over tau. Len of exponential, they will cancel each other. And len of 0.1 is equal minus 2.30. أحسنت يا محمد. We know the value of tau from previous problem, so minus t. Well, minus will disappear also. It will cancel. So tau multiplied by 2.3. Tau is 5.1, 10 to the power minus 3. Multiply by 2.3. And that is equal to 0.012 second. Well, as we defined it before, tau is 0.632 of the terminal, the time required to reach terminal speed. We just here tau is the time constant to reach 63% of the terminal speed time. So for example, if the time to reach the terminal speed is 1 second, tau is 0.63 of a second. It is fixed. It is fixed. And why it's fixed? Because we have an exponent. We have an exponent. So 1 minus 1 over e is a fixed value. It's always fixed, 63.2. That's correct. It's always fixed. Tau is always 0.32 of, not Vt, is 0.63 of the time to reach virtual. Not virtual. It is 0.63 of the time needed to reach terminal speed. طيب. So now let's talk about the second model. We said, let me remind you, we have two models. The first one we just did, force versus proportional to the velocity. Now the second model, when you have large objects, force is proportional to the square of speed, v square. It's not v, it's v square. So let's talk about it. It's interesting. And in a moment you will see why it's interesting. So first of all, let's talk about this main equation, this one. R is our resistive force. It is resistive force. So it's in Newton. It is in Newton. D, we call it drag coefficient. And depends on object's shape. That's the drag coefficient. طيب, what is rho? This one. It is the density of air or gas. Because the object is moving in air. طيب, what is A? A is a cross-section area. A cross-section area. Perpendicular to the velocity. Perpendicular to velocity. Let me try to explain it here. So if a person is falling down in a free fall, so the direction of velocity is like the direction of gravitational acceleration. Now we are talking about cross-section area perpendicular to the velocity. So if he is falling to the ground in this manner, then the area, the cross-section area is large. So he will have a lot of resistive force. But if he is moving like this, now the cross-section area is smaller and he will move with a faster terminal velocity. That is correct. That is correct. And you can see this a lot in the movies, that when he wants to go faster, he will just reduce his cross-section area. And finally, this is the speed. Because we said the resistive force is proportional to V square. لاحظوا drag force is constant, density of air is constant, cross section is constant, and then V square is constant. So R, it depends on R and V square. When you increase your speed, R will increase square of your speed. Square of your speed. And we know that, for example, if you want to go from Doha to North City at 100 kilometers per hour, you will consume much more gas if you go at 140 kilometers per hour. Yes, you will reach faster, but you will consume much more gas. Why? Because the resistive force will go as V square, not as V. So it's not linear. It's not linear. Consumption of fuel is not linear. In the car, it depends on V square. And I'm sure all of you realize that when you go faster in your car, you will consume more gasoline. طيب, let's do the same thing. Net force is equal mg minus the resistive force, which is half d rho a v square. We just reorganize the equation, so we get a alone, as we did previously, and the terminal speed a is equal to 0, so net force is equal to 0. So we end up with a terminal speed equation, which is equal to 2 mass of the object multiplied by g, drag coefficient, density of the air, and area cross section, which is perpendicular to the direction of motion, perpendicular to velocity, perpendicular to velocity. That means when you hear that this car maximum speed is this 200 kilometer per hour or 220 kilometer per hour, how we determine that? Well, maximum output for the engine will be equal to the drag force, and considering density of air, considering the cross section, and then you reach your maximum speed of the car. When we talk about falling objects, of course, it's always apply. Nothing on Earth move with increasing velocity. Always it will reach a point, if the motion is high enough, always it will reach a point that terminal velocity is constant. Terminal velocity is constant. Yani you don't accelerate forever in a free fall. The more you have acceleration of the gravitation, the faster you go, the more resistance force, until your resistance force equal to the gravitational force. It's not only the parachute, it's the rain, for example, or the hail. لما يصير عندنا برد, always it reach a terminal speed before it hits the ground. Always. يا عادل.
Doctor, like right now, what I'm thinking of, if we had an object which is too big, and therefore it has a lot of gravitational potential, and like there was another object fallen from far away, like totally far away, let's say in space, and our big object is like affecting the first object by its gravitational force. So what I'm imagining right now, that the object falling will accelerate and accelerate and until it reached like it won't stop. That's what I'm imagining.
It will stop, because the faster you go, the more resistive force you will have.
So I can't like accelerate forever.
That's correct, because you have resistive force.
But how to test that? Like
how to test that? It's we said experimentally.
Yeah, how to do it experimental? Like we don't have, like I can't imagine any equipment that enables us to do this type of test.
But why you don't have any equipment? يعني can you even if you have the strongest engine in a car, can you go forever? Can you accelerate forever?
This is not what I'm talking about. Let's just say we have a planet like bigger than Jupiter or bigger than Mars.
Yeah.
So it has like too much gravitational force, like too much gravitational acceleration. So it attracts the objects towards it. And the radius of its gravitational too big. Let's say millions of kilometers.
طيب.
And then we get another object fallen from these millions of kilometers until it reaches the big planet. So I can't imagine that this object falling will at some point reach a constant speed. Because in space there's no resistance, so it will keep falling forever, and that's millions of kilometers. So I assume it will reach really high speeds without stopping.
Well, you are neglecting rho. Rho is the density of the air or the density of the medium. So if there is space, then yeah, density is 0, and then basically there is no terminal speed. When you divide by 0, it's infinity. So that means terminal speed cannot be reached. But once you consider the density of the medium that you are moving in, then you start to have values for the terminal speed.
Okay, I got it. So in the scenario,
so in this equation, for example, when G is very large, يعني, the planet has a huge gravitational acceleration, then V terminal is also huge. That means there is a chance that you will never reach V terminal because it's very huge. And it needs a lot of distance to travel. You need to travel a lot of distance to reach your terminal velocity. So if G is very large, of course, V terminal is very large, and you need to cover a lot of distance to reach to your V terminal. Also, if the mass is very large, you need much more distance to reach your terminal velocity. So this equation does not talk about the time it will take to reach virtual. I don't know why it's virtual. It's velocity, terminal velocity. So this equation does not tell you when you will reach your terminal velocity, but it will tell you the value of your terminal velocity based on the distance it covers or the distance it travels inside the medium. Then you can say it will reach its maximum or not. But if you have enough time, definitely you will reach terminal velocity.
Okay, so Doctor, on the scenario I just mentioned, which is in space,
yes,
and the density in space is neglected, so we don't have density.
You don't have.
Does that mean?
That's correct. You don't have terminal. You don't have terminal velocity.
Yeah. Does that mean it is possible to reach the speed of light? Like, I know that's impossible, but talking about this equation and the scenario I just mentioned, it makes sense that an object could reach the speed of light.
An object with a mass cannot reach the speed of light. لأنه with the equations of relativity, once you start to go very fast, your mass start to grow very large, and then the force needed to accelerate this huge mass must be huge. So basically, you cannot reach with an object that has mass, you cannot reach the speed of light. And also you are forgetting that we divided the system into two systems because there is no one equation that it will discuss the whole circumstances in one equation. So we divide a small speed, small diameter, and large speed. But if you are talking about relativistic speeds, then it's a different model.
Okay, we have to move to relativity.
That's correct. That is correct.
Okay, thank you, Doctor.
Yeah. So now I have this question for everybody. Suppose that I took, for example, let us talk about Land Cruiser V8 engine. Land Cruiser V8 engine. when you put the numbers, you will reach a V-terminal speed for a Land Cruiser. Now, if we take the engine of a Land Cruiser and put it in a car which have less drag force, so the same engine, we can reach higher terminal velocities or a maximum speed for the car, although we are using the same engine. So I searched in the internet to understand that more, and I discovered that with cars, they use the same engine in different cars, and they reach a lot of maximum terminal velocity. So the first example, the Lotus Evora has the Toyota Camry engine, yet with the same engine, it can reach very high speeds. Why? Because the shape of the car has less drag force, so as a result, you can reach higher terminal velocities. Now Adil said Lamborghini and Audi R8 have the same engines. That is correct. Also, I discovered that BMW i8 has the same engine of the Mini car. And if you check actually this address, they have 10 examples of different cars using the same engine and reaching different high speeds or different terminal velocity. And again, why? Because we are talking about this equation. When you change the area cross-section of the car, and when you change the drag coefficient of the car, then you can reach higher terminal speeds even using the same engine. So if you are interested, you can go and check this website, that it will illustrate the use of this beautiful equation. So finally, in this chapter, we talk about an examples of terminal speeds. And the one I like the most is the hailstone, اللي هو البرد. When it has a diameter of 5 millimeter, half a centi, its terminal speed is 14 meter per second. وهذا يعني from the mercy of Allah سبحانه وتعالى, لأنه if the hailstone does not reach its keep saying virtual. If the hailstone does not reach a terminal velocity, it will destroy everything it hits. It will destroy everything it hits. So eventually it will reach a terminal speed, and that terminal speed will prevent it from being very destructive. And this is the end of chapter 6. Let me stop recording.